and I'll say it. So one thing to notice is I am recording these lectures. So I mentioned this in the syllabus, but lectures are all going to be videotaped, and they'll be available online. So after class at some point, you can go watch them. They'll be on YouTube. I would recommend, if you're watching them on YouTube, to watch an HD version, because I imagine it'll be pretty hard to read the board otherwise. But it's the first time doing it in this room, so we'll debug things as they go. Doesn't make up for lectures. You know, you can't ask me questions, etc. All the normal caveats, but it's a great resource to have, especially if you want to go back to some old material, see what's going on, or if you miss some classes too, you can watch the lecture video. So, okay, I am Professor Coulter. I am in computer science, and this is the first lecture on computational methods in sustainable energy. This lecture is going to be pretty much just an intro to the class, what the class is about, what we're going to talk about in this class. We won't get into any kind of technical details today. We'll do that all starting next time. But the big themes will be in this class will be, why do we care about energy, and sustainable energy in particular? Why should we care about this? Why is this a computational problem, right? It's normally thought of as not computational problem. What's the advantage of thinking about these in a computational manner? And finally, I'll do a little bit of both an overview of the course in terms of what you're going to learn in this course, what you will walk away with when you finish, and then also just sort of administrative stuff about the syllabus and these kind of things. If we have time at the end, we might off camera, but we might try to go around the room too and just chat and say, why you're interested in this course, what your area is, these kind of things. So that's optional at the end, and we'll see if we have time for that. But it's a small course, and kind of one of the benefits of those things. We can do things like all talk to each other. So all right, let's get started. What is this course about? And in fact, even more, what's this lecture about? So this lecture is going to cover really three things, as I mentioned before. First, I'll sort of talk about why sustainable energy. Why should we care about this issue? I imagine that a lot of you, if you signed up for this course in the first place, you probably already care a little bit about this issue, or at least know of it as an issue that maybe is worth caring about. So I won't spend too much time on that. But on the course of this, it's kind of good to at least have a little bit of an introduction about why we care about this problem, right? And then I'm going to get to why we should care about computation applied to this problem. And so here it's a little less well known of a point in some sense, I guess, in that a lot of energy is kind of thought of as physical systems, right? You study energy in terms of the physical dynamics of systems, and that's kind of what energy is. This course is about computation. And so I want to motivate then why we should really care also about the computational elements. And I'll give two kind of examples there about what sort of things have been affected by computation. But really, I think the future is what holds the most promise here, in that you guys are the ones that are going to be kind of making the really compelling examples about why you need computation for energy. So that'll be the second bit there. And then finally, I'll talk about what we're actually going to study in this class then, right? What will you learn through this class? What techniques are we going to learn? What sort of, and then also kind of the details of just kind of what projects are you going to do, what are the homeworks like, etc. So I'll stop here. Are there any questions already? I'll try to cover everything kind of over at the end. If there are any questions, I'll hopefully get to it all. But maybe we'll just jump right in and say, why do we care about sustainable energy? As I said, probably people here, you may already have maybe already predisposed to care about this problem. But sustainable energy is kind of a buzzword these days, right? And I think it can mean a lot of things. It means a lot of things to different people. But I think a good definition is from 1987, a UN report called Our Common Future. And this talked about sustainability as a whole, but I think it applies well to sustainable energy as well, this kind of definition. So I'll just read it. It says, sustainable development is development, or you can, I guess, substitute energy instead of development here if you want to. But sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. All right, so that's a very kind of vague definition, but I think it's a good one too, right? Because we are talking kind of vague terms here. When we talk about sustainable energy, we want to talk about energy that is able to provide for our own needs while not sacrificing the needs of the future or sacrificing the environment of the future. And that is very broadly what I mean by sustainable energy. So why is this a problem? Well, if you look at the history of energy consumption in the US, and the world actually looks even more dramatic than this in some sense, but if you look at the history of consumption in the US, you'll see that this goes back to 1850 and to about 2010 here. And basically energy consumption goes one way, it goes up, right? Maybe with a couple little bumps here from the oil crisis and the Great Depression here. That's basically the only thing that can really slow down, it seems like, our increase in consumption. And if you look here, these three portions here, this is coal, natural gas, and petroleum, these are all fossil fuels, and they're all ultimately finite resources. Now, how finite they are is a question of a lot of debate, and we won't really get into that. But they are finite resources. These are, in some sense, unsustainable, right? We're going to use them up. They've been built up over millions of years, longer than that, hundreds of millions of years. And they're not going to last forever. There is a significant portion of the energy in the country that is what I would call sustainable in some sense. And that's things like hydro, nuclear maybe, depending on how fast we're depleting resources, and then biomass. And biomass here actually means not things like biofuels, but more things like wood for heating homes. And these, in some sense, are sustainable. And the rest, about 87% makes up this portion, and the rest makes up that. But actually, I guess if you think about renewable energy, right, you think about things like solar and wind and geothermal. And if you really kind of squint, you can maybe see a couple green pixels up there on this chart here. It is a tiny fraction, less than 1% of our energy comes from renewable sources right now. And when I say energy here, I mean energy both in terms of electricity, but also fuel for cars, heating for homes, these kind of things. And then by that metric, it's still less. It's about 1% right now of our energy from these sources. So we can look at this in a little bit more detail here. And I won't go through this slide in too much. It's actually kind of hard to see. Maybe I don't want to dim the lights too much because then it'll be hard to see the board. But anyway, I actually won't go through this picture too much today. I'm going to go through it in a subsequent class. But essentially, you can also look at where this energy goes. This is a figure from Lawrence Livermore National Labs, and it shows essentially of all the different sources we have. So I'll just read it here. You won't be able to see the labels here. But this is petroleum, this is biomass, coal, natural gas, and wind, geothermal, et cetera. And it shows kind of where they're being funneled into in terms of our consumption side of things. So it's good to understand also not only what are we using, but where is it being used for. So for example, a lot of petroleum is being used for transportation, especially one of the sort of only uses these days of oil here, because there isn't much of it. And if we're going to use it, we might as well use it for transportation. There's also a lot is converted to electricity, of course. And this whole chart also shows kind of what portion of the energy here is actually used and what portion is called rejected energy. And that's just basically if you generate energy in a coal plant or something like this, there's going to be a certain amount of energy you are losing by that generation process. And that all goes to kind of rejected energy versus this energy actually is being used here. This figure is much more readable in the slides. If you want to take a look at it, just see what it looks like yourself. You can do that. But let's actually go back to this slide here and take a little bit closer look at this sustainability of some of these resources, right? So let's look at petroleum in particular. And this is US produced petroleum, not imports, but just US produced petroleum. And it peaked somewhere in the 60s and 70s. And it's really, as much as we try to fight it, when something like this happens, it's unclear if it ever is going to, rebound and really we're going to start having a whole lot more oil made in the US. And this is just a matter of resources, right? We don't have that many untapped petroleum resources compared to other parts of the world. And so while it's easy to talk about peak oil in terms of a global phenomenon and when that might happen, if that's going to happen, et cetera, I think that it's pretty clear from this that actually peak oil in some sense has already happened in the US. So we've already reached that in terms of US production. Unless something major happens to change this in the future. So the other resources, at least coal and natural gas, it's not so clear for those, whether we're really losing these or whether we're we have a whole lot. With the advent of fracking, there's potentially a whole lot more natural gas right below us, in fact. And so these reserves there's a lot of debate about how much there is left of these reserves and how long it could sustain us. But they are finite resources. They do get depleted, and we have to keep this in mind when we talk about these resources. I think actually the more compelling argument, though, in some sense, is not just the fact that they're finite, but the effect they're having on the environment. And this, again, this course is not going to be all about debating the science of climate change or anything like this. But I'll just present a few facts here, because this is really a major concern about why we are worried about the energy problem. And why it's a bad thing, potentially, that we are pumping so much CO2 and burning so many fossil fuels and pumping so much CO2 into the atmosphere. So this graph now shows what's caused by that increase in fossil fuels. So this shows the CO2 levels in the atmosphere, how much carbon dioxide in parts per million in the atmosphere. And for the last 1,000 years or so, it hovered kind of constant. And then right about the time of the Industrial Revolution, it not surprisingly spiked up and has been growing ever since, very, very quickly, at a rate which really has not been seen before historically, even in the geological past. So we can also go, well, so this looks kind of intense here, but just to sort of put this in a little bit more perspective, if we go back even further and try to get estimates of CO2 concentration in the atmosphere for the past 600,000 years, I think actually this graph was on the walkway by CNU that had this little light drawing of this chart here. But essentially, sort of a sad thing is we were actually already at kind of a high point to begin with of our CO2 levels. So this is sort of, it's been bouncing around some, and all of a sudden it's spiked up much, much faster. And so this graph you saw on the last page is this little blue line here. You can't really even, it's like a straight line in a graph like that historically. So we really are in new territory here historically. And one of the biggest problems of these energy resources is that they are causing this. And that part I think is pretty undebatable. Now there is there is some debate, I wouldn't say debate, but there are some arguments at least about climate change. And so just to understand a little bit more about why people think this is a bad thing, what's important here for in terms of CO2 causing potential increases in temperature is what's called the climate sensitivity. So this number, which I'm calling delta T2x, is how much the temperature is going to increase on average if we double CO2 concentrations. And this is important because we are in fact doubling CO2 concentrations from their baseline that they were a while ago. We're well on our way to that. And if we bump up the temperature of the Earth by 2 to 4 degrees Celsius, this would be a very bad thing, right? This causes all sorts of major problems, all sorts of major major societal and just environmental problems. And the latest IPCC 2007 summary estimated that this number, this climate sensitivity, is probably somewhere between 2 and 4 degrees Celsius. Now, if you've heard some about how there's so much uncertainty in these forecasts, because that is a big range, right? 2 to 4 here. The reason why that is uncertain, and why there is uncertainty, and I should say the climate scientists are very well aware of this uncertainty. But the reason for this uncertainty is that if you look at what this temperature difference comes from, it comes about 1/3 to 1/2 from the actual CO2, and the rest comes from feedback effects. Like, if you raise the temperature of the Earth a little bit, this causes more water vapor to be released by the oceans. Water vapor is itself a warming agent, and this will cause more warming. So getting this right is by no means easy. And this is what climate scientists do. And this is why, and these kind of models, which are actually quite complex, are why they think it's in this range. But this is where the uncertainty comes from, largely. So that's all we're going to say about climate change in this entire course. It's not at all about climate change. But climate change is a motivation for these things. And so I think it's good to at least understand the basics of what's happening here. And if you're interested, there's actually a lot of very good kind of intro-level books about this topic and kind of explaining it in easy language, but also in language of an undergraduate level. So it's not just, you know, for the general public. It's actually quite mathematical too. So if you're interested in those, just let me know. Okay, so that's it for these kind of things. But just one more kind of sobering note here. Think about energy for the world now, and we look at the actual population of the world. This is another tricky issue here. Right, the US consumes right now, I think it's about 18% of the energy in the world. And we're about 4% of the total population. Look, North America is this little bar up here. Now, population forecasts are very hard to do in the long term. But in the short term, they're actually quite accurate. And in the next, I believe, 20 years, there are going to be 500 million more people in Africa, for example. That's actually very easy to predict on that level. So that's a whole other US and a half coming up in the next 20 years. And if we start talking now about resources of energy, not just for the US, but for the entire world, if we want people to live in a lifestyle at all sort of like what we are accustomed to here, and we are sort of also in the top crust of the US, like many of us, this becomes a much trickier issue, right? And changes have to come. Big things have to happen, and this is really an issue that is one of the grand challenges facing the Earth right now, facing society. Okay, so I'm going to get off my soapbox now. I'll talk about more practical things from now on. If you are interested in these kind of topics, I'd really recommend checking out this book. It's called Sustainable Energy Without the Hot Air. It's a book by David MacKay. David MacKay is actually was a machine learning person, but has since decided that he wants to pursue energy kind of from a physical standpoint. He didn't like how a lot of the analyses of energy weren't very scientific, right? So there was this big campaign in England to get people to unplug their mobile phones to save energy when they're not being charged. Sorry, mobile phone chargers when they're not charging anything, right? And so this is one of the things you can do to make society better and to make us more sustainable. And he was very annoyed by this because essentially this is a tiny, tiny fraction. I mean, it's inconceivably small of a fraction compared to our actual consumption. And so he got very, very frustrated with this and wrote this great book that essentially goes through the physics and looks at how much energy it fundamentally takes to provide certain services to us, like cars and flying and heating, cooling, etc. And he goes through all of these things, says from the physics why they're necessary, and then he adds up from renewable sources, just suppose we want to live completely from renewable sources, he adds up kind of a big stack here. If we kind of ignore the feasibility of a lot of things, what if we just assume we can devote, say, a fifth of the country to solar panels, how much energy will that actually produce us? And it's a very, very good book. It's very readable. I highly, highly recommend it. It's also free online at this site here. So you can download the PDF and take a look at that. Okay, so that's all I'm going to say about energy. I know that, or about sort of the motivation of energy. Say a lot more about energy itself, certainly. Are there any questions on this stuff? I know this is sort of a very, very high-level overview, but by all means, if you have any thoughts or questions, ask away. Okay? All right. Moving on then. So the next topic is now, why computation? This is clearly a big problem, and clearly also it's one that's not fundamentally a computational problem. I think a lot of people would I mean, actually, I take that back, but it's not one that's only a computational problem, certainly, right? It's not as if we can solve some big computation, some big computer program, and all of a sudden solve the energy problem, right? This is a physical problem. We need to actually build things to solve this. We need to actually build lots of things to solve this. So why should we care about computation? What's the role that computation is going to play in all of this? And I think it really will play a fundamental role in all of this. And to motivate that a little bit, I'll give two examples coming up that are a little bit much more concrete. But just to give a little bit of insight into this, imagine you, and we'll just say you're in the US now, and you want to supply power to the entire country. Right? What this involves is taking our 5,500 power plants, telling them all how much power to generate, such that, and they have a capacity of about 925 gigawatts. If you haven't seen energy units before, or power units in this case, we'll go through all those too, but gigawatts are a unit of power. It's a production of a rate of energy over time that they're producing. And it's kind of so it's instantaneous. This is the amount that we're consuming per time at this moment. So you get to schedule how you're going to turn on these different power plants, to what levels, such that the power flows over 172,000 miles of transmission lines, each of which have some limit about how much they can transmit, or how much is able to go over those. And you have to provide these to 83 million homes and maybe 5 million buildings that all want instantaneous power. Right? When we turn on a light switch, we don't want to wait a little while for something to happen. We want light to come on right then. So all of these sources, really whatever they're doing right now, you have to turn on power plants to account for this, while meeting all these constraints here. And as you can imagine, I'll talk about this, we'll actually go over this a lot more in this class and cover how this is done precisely. But as you can imagine, this is already a computational problem. People are already solving this with computational methods. So in fact, computation already plays a huge role in energy. But now add to this mix a few more new things. Right? So first of all, let's add the fact that we have right now about 50 gigawatts of installed wind capacity in this country. That's pretty small right now compared to the total capacity we have, right? About 5%. What we're hoping to have is actually much, much more than that. Talking about, a lot of states are talking about 30% renewable penetration, things like this. And the difference here is that these wind and solar, it's mainly wind thus far, but there's some solar too. These renewable sources, which we sort of associate with sustainable energy, right? Because these things, or at least the resource won't run out, even if we have to rebuild some of the actual mechanisms themselves. And the difference here is that we can't turn these on and off, right? We don't really have any control over them. I guess we could turn them off, but we can't turn them on more if the wind isn't blowing. Right? They're just going to produce the power they're going to produce, and we don't know what that's going to be. And right now, we sort of have very little of it, so we can kind of buffer it a little bit by just, having some generators that kind of respond to this very quickly. But if we get more and more of these things, we're going to need more and more to be able to account for the uncertainty in these sources. And this is even a bigger computational problem, right? Now we have planning under uncertainty that we have to do. I don't know what the one's going to look like in 30 minutes, in an hour, etc. How should I schedule my plants right now to account for this? Plants also take a while to start up sometimes. Maybe you can't start a plant, get it going for 6 hours or so. What do you do then? So this penetration of wind, which is kind of what we associate with sustainable energy, right, is making computation even more of a problem than it currently is. Another thing's happening too, which is things that are great advances are happening in sensing as well. So right now in this country, we have about 30 million installed smart meters. Smart meters are meters on a home that monitor the energy of that home. About 30 million of them. And all just kind of recording data. They could record it up to every second in a lot of cases. They don't right now because they can't even store that much data. But what do we do with all that data? We have much, much more fine-grained monitoring than we've ever had before, really in the history of the world. This is not just true for energy, it's true for everything. But in energy, we have it too. And how can we use this fine-grained monitoring to actually perform better on some of these tasks here? Can we use it now to actually understand more, say, what the demand's going to be predict that, or to predict how we should schedule these power plants differently to make it more efficient, use less energy, etc. And this is the way that computation really, I think, will become more and more of a focus going forward. Because we have more sensing and because we have more uncertainty in our resources, we're going to need computation more to actually achieve a lot of these goals of transitioning over from kind of the system we have right now to one of what we think of as a renewable, sustainable energy system. I should add, too, a big problem here is that it would be nice if we could just take this energy and store it into a big battery, right? That would kind of eliminate a lot of the need for maybe a lot of the planning uncertainty. But right now, at least, we don't have that. We don't have batteries that are nearly that big on that level. And so we need kind of computational ways of dealing with this and of handling these issues. So now I'm going to talk about two kind of different examples. This is a little bit about how computation has, or computation I think will play a role in the future of energy. But there have been success stories too. Right? Computation has transformed energy already. And there are a few examples of this that I think are sort of very, very pointed. There are two stories I'm going to tell right now, which are both highly simplified stories. Don't take them as a history of these different fields. But I think they do highlight kind of how exactly computation not only will transform energy, but already has done this. So to start off, I'm going to talk about this rise in wind power. So, and actually, this is going on to 2010, so we even have more right now, right? The last slide said we had more than that as capacity, so that's even good. But basically, wind power has been taking off recently. There's been much, much more installed wind in this country. And why is that? And I mean, a lot of it is due to the regulations we put in place here and due to kind of programs that we've said to encourage this kind of development. But basically, in the last 12 years, wind has grown from almost nothing to a reasonable amount of electricity being provided by wind. So what's happened in the last, say, 10 years, or maybe even importantly, in the last 40 years to actually allow for this to happen? Because these things take some time to actually go from development to deployment here. And to do this, I'm going to go through a little history of wind turbines and see what they've been in the past and what they're like now. And this is the first known wind turbine ever. I don't know if it was actually built or not. I think no one knows if it was built or not. It's Heron's wind wheel. It was Heron's wind wheel. It was from the 1st century. And essentially, it used wind here to move the pipes on an organ and play an organ song. Just a drawing of this. It's not a real thing as far as we know, but this was, as far as we know, the first known schematic of using wind to actually power some mechanical system. So kind of a cool bit of history about how long we've had wind, so why did it take so long for us to start using it to a large degree. Well, jumping far, far forward, and I'm skipping a lot of things here, but jumping far, far forward, what you might be more familiar about when you think of windmills is things like this. This is a smock mill. I actually forget what, I think this is from England, but I take that, I'm not sure about that. And these essentially developed in the latter half of this millennium, I guess. And they essentially used wind power to mill, usually grain, right? So moving beyond just, say, blowing an organ, we're doing something useful with these things now. But it's sort of, as you can imagine, it's kind of easy to just have some wind blow on this. It moves a big grinder, and that grinds flour. Use water for the same thing, but wind is a nice thing if there's no river nearby. Then, I mean, jumping even more forward, in the 20th century, people started to think about how to use wind to actually make electricity. Right? It's a natural thing. We started to use electricity more. Let's think about how we can use this wind power to actually make electricity. And this is one of the more famous examples of this. This is the Smith-Putnam turbine. And it was 1.25 megawatts would generate, a capacity would generate, which is actually a very, very big turbine. This is the same scale as a lot of wind turbines that are made today. So we're not only generating electricity, but we were doing it at a pretty decent scale here. This was in the 40s. And what happened here was that we built this machine, And then one of the blades fell off. Right? So in 45, the blade snapped off, and that was the end of it. So probably not what you want to happen every 4 years with a big wind turbine, right? So while we sort of had a lot of the aerodynamics down, and actually you'll notice these blades, if you can see really closely here, the blades are a lot like airfoils. And actually the aerodynamics to describe a wind turbine were known by the turn of the century, turn of the 20th century, by 1900. Yet we still couldn't build a wind turbine that wouldn't fall apart. Then what happened a few more years forward is that you get wind turbines like this. This is in the 70s now. And it's a experimental turbine built at UMass. It's called the Wind Furnace 1. It was called a wind furnace because actually in the initial design it was going to make electricity to heat a house, which is a horrible use for electricity, as we'll see shortly. But that's what they were going to do with it. And this turbine was kind of exemplary because all of a sudden we have a lot of the characteristics of modern wind turbines. We have things like optimal blade shapes. The blades here are, you see, they're sort of feathered down. And they're actually also twisted a little bit. We have things like variable speed operation. It's not always spin at the same speed. It can actually change at different speeds depending on the incoming wind speed. We have the ability to control power by changing pitch. And we have a microcontroller that actually controlled this system. Now, in some sense, what happened here, the reason why this became possible all of a sudden was computation. Right? So obviously the computer-controlled thing, that's computation, quite clearly. But the other things really are too. Because what happened in 1974 was that Wilson Lissaman published this book, which became sort of well known. It's called Applied Aerodynamics of Wind Power Machines. And again, don't take this as sort of canon about what is actually the history of wind turbines. This is a very specific story here, but just want to highlight that again. But essentially this book went through the aerodynamics of wind, which, as I said, the actual mechanics were known for a very, very long time. But what this book had was code that actually simulated all these things on a computer. And all of a sudden, and then it says, I think one of the first pages says, the advent of the digital computer makes preparing general performance plots of wind machines easy. So all of a sudden, what we had is the ability to actually simulate these things using simulation codes. And that fundamentally changed how wind progressed. We went from these systems that we just kind of put up there, hope it works, maybe the blade falls off after a little while, to really understanding the strains involved, the aerodynamics involved, not because the math is that hard, but because we can do it analytically. Or at least, sorry, we can do it computationally. And now, in fact, it would be silly to even talk about wind power without talking about computation. Right? So wind turbine blades are designed based on sort of these panel methods that actually look at the strains of how aerodynamics are going to affect the blades. There's been a lot of work in simulating wakes of turbines. So how do you actually know what the aerodynamics are going to be of a turbine as it spins, say in unsteady wind? This is actually much harder than those first computations now. How is the wind going to change? How is the actual wake going to flow off the back of these blades here? It's all very hard issues, but computation really has changed how we approach these problems. And of course it has to. It's changed so many things. We'd be silly if we didn't try to use computation to address problems like this. And in fact, the only way you can build great big turbines like this one, this GE 2.5 megawatt turbine, and have them last for quite a while, you see them popping up all around the country, is through computation. So that's one example, I think, of how we really have affected sustainable energy through computation. I'm going to give one more, and then I'll get into the actual topics of this course. But this next one, we're not going to cover wind too much, maybe a little bit about forecasting wind, things like this. But this next one we are going to cover here. And this is the advent of power markets in this country. So again, a little history lesson. In 1935, as part of the New Deal, that was at the end of the New Deal, but anyway, 1935, the U.S. enacted what's called the Public Utility Holding Company Act, or PUCA. And this mandated that all electricity generated would be controlled by a single monopoly in different regions. So a single monopoly controlled the generation, distribution, and the transmission. Single company, like Con Ed, owned it in some places, and other ones owned it in other places. And then, in 1992 and 2005, this law was repealed. And this, and I'm not going to actually, there are some people that kind of disagree with how well this has actually worked in practice. But at least in theory, the repeal here, it offers the potential to compete in a market for power generation. And all at least the potential efficiencies that come along with that, right? Where you can have different companies competing to give better prices on generation, so hopefully make things more efficient, etc. Now, how could we possibly just go ahead and repeal these things? The difficulty with power markets is they don't operate like a normal market. So in a normal market, and we'll cover this in a lot more detail here, but essentially, if you're a consumer and you want some amount of an item, some 1,000 units of whatever, what you can look at is different producers will have different costs of making those items. These costs may be lower or higher for different numbers of items. Right? So maybe if you're going to make any, it costs a certain amount, or just to run the plant, say, this one kind of starts off at kind of a high price here, but then goes up more slowly, whereas this one starts off at a very low price, but goes up higher. And very, very informally speaking, if you kind of have a system where you place bids for, how much would you be willing to pay for this, how much will, these producers can say, well, I'll sell you this much for this amount of money. These transactions, under certain assumptions, will actually converge to the optimal market price, and you will, in fact, get a situation where you're paying kind of the best price possible, assuming there's fair competition and all these kind of other technical conditions that you need to make this happen. But this can happen in practice, right? It's reasonable to say that I'm just a consumer. I want to buy a computer. I'm just going to look at different brands, pick the cheapest one. They'll all compete against each other, so that'll kind of work it all out, and the market will kind of stabilize that way. Very, very informally speaking. We'll cover this in a little bit more detail later in the class. But the problem with the power market is this just clearly would not work, right? You can't say, well, I'll turn on the light now. How much do I want to pay for this much power? I'll give you this much. And another company says, I'll give you this much. Meanwhile, your lights aren't on that whole time. So that wouldn't work. And unlike a lot of products here, we can't store energy yet in significant quantities. So the thing with a computer that makes it nice is if you don't want to buy it today, you can buy it tomorrow because you just store it in a crate. You can't do that with energy. It's generated right now, or there's no real use. Especially something like wind, right? If the wind's blowing and it's going and you don't use it, well, that's sort of that. And there are also constraints on the transmission grid. So you can't just generate power however you want in different generators. You have to ensure that not too much is going to pass over any given line, or it might melt, and that would be pretty bad. So all these things make power markets very different from a typical market where you just have some goods, you want goods, and you let it all work out. So how is this even possible? How could we possibly satisfy a market like this? Well, in the 80s, just before that law was passed, there was a very well-known book that came out. It was by Fred Schweppe, Michael Karamanis, Richard Tabors, and Roger E. Bond. And this is sort of a seminal piece of work here. And there was a lot of work building up to this, I should say. This is not the first thing that has appeared. But this is a very well-known book. It's out of print right now, so if you want to buy it, I think it costs about $400 on Amazon. You could look for it. I tried to buy it myself, but they're even at MIT, and I couldn't even find it when I was there. But I wouldn't recommend buying it. But seminal book nonetheless. And this book laid a computational framework for how you set up a market for buying and selling power in a way that respects the transmission grid and allows you to do this and allows you to always have power if you want it, while still allowing for at least some degree of competition in the market. Again, there's a big body of literature other than just this that says similar things, but this is kind of one of the more famous books in this area. And in fact, this is exactly what's happening right now, what's described in this book. So right now, our RTO, our regional transmission operator, which is called PJM. PJM is a company that serves, coordinates power generation and consumption for Pennsylvania, New Jersey, Maryland, and a couple other outlying areas. And what they do is is it 15 or 5 minutes? 5 minutes here, yes, okay. Every 5 minutes, they take bids from all these different generators across this entire region. These are what allow it to kind of have its open market. These generators put in bids about, I'll say this much power for this much money. They solve a giant optimization. They look at demands too, so look at how much people are actually using. And they solve a giant optimization problem that says, okay, given all this demand and given all this possible generation, given these constraints, here's how we're going to tell each generator to turn on or off, or how much they should be generating. And in this class, we will cover exactly how this is done. So you'll learn how this actually happens, and you'll learn how you can actually do that scheduling of power in a way that makes sense. And in fact, they are already doing it. Right? So these computational methods have really transformed how we get our power already. Okay, so that's enough of why computation, I think. Because in some sense, I think the best stories have yet to be written. Right? I think people here are the ones that are going to go off and create the really compelling applications of computation applied to energy and sustainable energy. And it will be a no-brainer that we're going to have to use computation to address these things. Okay, any questions on this part before I get into the actual structure of this class and what you're going to learn here? Yeah?
I have a question about the special probability of the power market. Like they have to have a certain amount of fixed supply, right? Like in winter, they cannot just, a company can break down, but the power plant has to provide certain amount.
Yeah, so there's all sorts of services that sort of basically guarantee that you have to meet your commitments if you're going to bid into this market. If you don't, you have to buy it from someone else.
Yeah, how the computation make sure that.
So I mean, that's kind of a combination of computation and then regulations too. Because you need the regulations to basically say, if you're going to place a bid into the system, you better follow through on that. You better not just put a bid in and say, oh, we can't do it. Our plant broke down. Even if you have to pay more, you better buy it from someone else, say. So maybe someone in a different region, someone across, in Canada or something like that, from or New England or Ohio. That is the combination, then, I think, of both these problems being solved, but then also the regulations that are in place to ensure that they will, in fact, people will be honest in these transactions. Because you are required to kind of meet this instantaneous demand, there is a bigger burden of honesty on the participants here, right? Because you can't just, unlike if I start going to a computer manufacturer and I order one, they don't send it to me, that won't work very long for them. But when it comes down to it, I can get my money back if it takes some time, whatever. Here, if the lights don't go on because someone messed up, we have a power outage, that will be a really bad thing. You have to combine those two things. Okay, so what is this course about? I think there are sort of two ways of viewing the course. One's kind of from a top-down perspective, and one's kind of from a bottom-up perspective. So from a top-down, big picture perspective, if you want to control a system like power distribution, or like even a single renewable plant, or even anything that has to do with these large physical systems, there are really two key components involved. Right? On the one side, there is modeling and prediction. How can we model these systems? How can we predict what they're going to do if we take certain actions? And on the other side, there's control. given these models, how do we actually take these actions in some sort of optimal way to produce the desired effects? Are people familiar here with these different terminology, modeling and control, meaning controlling systems? Nodding, yes. Okay. Now, the modeling side of things kind of breaks into two different categories, I think. When you don't have a good model of the system, or maybe something that's really hard to predict, like, for example, the demand of electricity on any given day or in an hour. It's kind of hard to predict. Right? You can't write down a sort of first principles model from physics about how much demand we're going to use. Or if you were, it better be a really complex model, because it has to simulate human consciousness and all that kind of stuff too. So some things are just kind of fundamentally hard to predict. Yet, from certain data, we can make very good predictions about what they're going to look like. And this whole field of predictions kind of from data, when we don't have a model, I'm calling machine learning. And this is kind of the terminology that computer scientists use to talk about this stuff. But there are, of course, many others. I think statisticians, with calling it something new, I think would be a little bit funny there, because they've been doing it for hundreds of years, right? But that's what I mean by here. We're going to look at computational and I think that the new thing in machine learning, really, if you even want to call them different fields, machine learning and statistics, is that this machine learning focuses on computational methods for making kind of predictions like this. The second part, and so the first unit of this course is going to be on machine learning. How do we make predictions about things like electrical demand when we can't really write a model a priori for it? How do you predict those things? The second part of prediction is when we can write down physical laws to describe systems. It'd be silly to try to learn from data how circuits behave, in some sense, because we know how circuits behave. Maybe there are a little bit of noises that we can sort of adjust to over time, but fundamentally, the laws of electric circuits are actually pretty well understood, and also have been for a long time. And so we also want to use, for systems where we know the laws behind it, we want to use physical modeling to understand what's going on. This is the second unit of this course here, which is going to be about electric power systems. When we talk about energy, I am going to be focused mainly on electricity here, and I'll talk about the motivations for that in the next lecture. But for something like electricity, at least, it's of course very important to understand how electric power systems operate. And the last unit is going to be on control then. That's sort of a question of how do you put all these things together, these models you have here that combine maybe predictions from machine learning methods, predictions with power systems. How do you put this all together to actually make the system do what you want? Maybe use less energy, produce less greenhouse gases, things like that. How do you achieve that using whatever knobs you have on the system? And that's what the control portion is about. I also have some time reserved for guest lectures or special topics. If people are interested in certain things, we can kind of come up with a few, I think 2 extra lectures as well. But that's kind of a top-down view of the course, right? The overall idea about controlling and modeling and controlling systems. And I should say that other than this unit here, the electric power systems unit, probably a lot of this is equally applicable to almost, well, not every other, but a lot of other physical systems, right? So this is a course on energy. This portion is sort of one of the energy-specific ones. These other things are more general techniques that are kind of state-of-the-art techniques about how we model and control general physical systems. And I should add, though, that the sort of the characteristic here is that we're going to use examples from energy to kind of illustrate both these two topics. And so they will be tied into energy, even though they are general techniques you'll be familiar with. Okay, so then that's kind of what the course is at from a high level. From a lower level, this course is really about applications and algorithms. So much more concretely, you're going to learn about a lot of things in this course. Right, you're going to learn about things like how to predict electrical demand using machine learning methods. How do you estimate what sort of renewable resources are going to be available in the future? How much wind is going to be blowing in 6 hours? How can you estimate that? How can you analyze and understand energy consumption in buildings? We'll have a little unit on that. How do you compute things like power flow, these power markers I mentioned about? And how do you optimally control things like distributed storage? So if you start to have some small amounts of storage available in your system, how do you actually control those, turn them on and off, say when to pull in and when to push out energy to actually control the system and optimally in some sense? And so all the things we're going to cover in the course. And we're going to cover how you do all these things, and through the problem sets and assignments, you'll become very familiar with all these application areas relating to energy. And the other half really is the algorithms. Right? To achieve these things, we're going to use a pretty broad class of pretty advanced algorithms, which really are the latest methods in machine learning, for example, in time series prediction, etc. So we're going to talk about linear and nonlinear regression and classification methods. This is how you make predictions. They're either real valued or maybe discrete valued. We're going to talk about convex optimization a whole lot. Optimization is how you actually formulate a lot of these problems. Maybe not always convex, but sometimes convex. And how can you actually solve these type of methods? How do you solve control problems? Well, a lot of it boils down to convex optimization. And we're actually going to use not just write down the formulations, but you're actually going to solve the convex problems using some libraries that are very recent that basically pretty quickly in MATLAB lets you solve a challenging optimization problem. So you'll learn how to do all that. Also things like time series prediction, right? A lot of what we're talking about is forecasting things to the future. So you say you know demand up to the current point, how do you predict what's going to be in the future? This is a time series prediction problem. And the temporal aspects of it are very important here. Things like Newton's method, which is kind of one of the fundamental ways of how you actually solve a lot of these problems. MPC, or model predictive control, is how we actually solve a lot of control problems in a way that actually is not optimal, but is very, very good for a lot of different problems. It essentially involves every time you solve a big optimization problem, it describes your control task. And so you'll actually solve model predictive control tasks and problems in your homework assignments. And then things like mixed integer programming, when things are not convex anymore, how do you actually go about solving them in a way that might be, worst case, have exponential time complexity, but in general can be pretty fast for small size problems. But the important part that I do want to drive home here is that when looking at these algorithms, we're going to be applying them as much as we can to real world data. So I think grounding all this work in real world energy problems is really how to make it the most relevant to the domain at hand here. So we're going to use real data from the Pennsylvania electric grid about demand, about wind, things like this. All real data to actually apply these algorithms and get predictions about what's going to happen. And so you will be experts in all of these things by the end of the course. Any questions here? This is a whole lot of topics I just put up here, so if anything I said didn't make sense yet, hopefully it will by the end of the course. Questions? Okay. So, let's talk about the boring stuff now. And let's see what time it is. Am I already, what time is, okay, no, I have half an hour more. Okay, so boring stuff now. What is this class? What do you need to take this class? The class prerequisites I wrote on the web page. Is everyone, first of all, everyone, backing up a sec, does everyone in this class right now get an email last night from me? Raise your hand if you did not get an email. The camera can't see you, so only I will know. Okay. Guess that's fine then. So everyone's on the list. Everyone knows the website of the course then. All the material will be posted there. Lecture videos will be up there after classes. The lecture notes will be there before classes. And you can get all your information there. I will send out emails to the addresses I've been sending it to. People have questions. I'm considering using Piazza as a discussion board for the class. I'm not sure if it has really, maybe I'll ask after the class, after we turn off the camera, if anyone has experiences with that or not. I'm not sure if it's easier just to email people. There isn't a huge class, so maybe it's just easier just to email, but we'll think about that. But anyway, on the website, I listed 2 kind of vague prerequisites for this class. One was programming experience, and one was linear algebra. And these 2 really are going to be kind of core technologies we use throughout the course. You can probably learn some of it through as you go through the course, especially if you're very experienced in language other than MATLAB, just haven't seen MATLAB before. But you will need to use MATLAB for this course. The libraries we use for optimization are based in MATLAB, and there are not very good ports, unfortunately, to any other language, which is kind of a shame because they're very nice tools, and it'd be nice if they were kind of in a purely free environment. But MATLAB is quite nice for writing things like this, and so we're going to be using it for our programming assignments. If you are really, really bold and just can't stand it, you can use something else, but you're kind of on your own for how you actually solve a lot of these problems, and it will be tough. So some programming experience is necessary because if you're learning programming for the first time while taking this course, it's probably going to be pretty tough. But again, we're going to use pretty simple MATLAB here. There's nothing too complex in the MATLAB. So a program like this, if you can understand this after thinking about it a little while, you can probably be fine. Or even if you just, after thinking about it for a while, after going through each, the man page for each of these calls or the help page for each of these calls, if you can figure it out then, you probably will have enough to do a lot of what we do in this course here. So actually, we can just go through what this program actually does here. Not what it will produce when you run this, because it's actually kind of cool if anyone wants to try it, what it will do. If there are any guesses afterwards about what it will do, let me know. But what MATLAB is very good at is building matrices and vectors and operating on them. So this call here, this P equals blah, blah call, creates a matrix, P, which is equal, I should write a little bigger than that. It might be hard to see in the video. P equals a 3x2 matrix, where the first row is going to be 0, 0, second row is 0.5, 1, and the third row is 1, 0. So the little semicolons here denote the end of a row. This next call creates a big matrix of all zeros. So it sets x to be equal to 0, but 0, which is a matrix in R, 50,000 by 2. Okay, that's kind of beneficial. X is in this thing where x ij equals 0 for all I and j. Kind of fair representation about what this is doing. And then it does the following thing. This line's the most complex one. So it loops now over from I, a variable I, being equal to 1 to the size of x. The size of x being the first dimension of x, that's the 50,000 here, minus 1. So it loops over I being 1 to 49,999. And each time it does the following. It sets the I plus 1 row of x to be equal to half of the I row of x plus half of a random row of p. And the way it gets a random row of p here is we generate a random number. That's a random number between 0 and 1. Multiply it by 3. Round up to the nearest integer. That'll be an integer between 1 and 3 with random probability. Equal probability to each one. And then we take that row of p. So this is the algorithm that we're running here. And then we plot what it looks like. Does anyone actually know what this will look like? Yeah. Okay. Can't say that. Okay, it looks kind of cool. I'm going to try it out. When you get MATLAB installed, copy this from the slides. It's nothing to do with energy or anything, just kind of cool. Yeah. It is, but not quite. I mean, it's something kind of interesting. You'll see what it looks like if you try it out. As a test, when you get MATLAB installed, just try it out. MATLAB, I believe here you can get for free, right? Everyone, you can download it from computing services. So get it, install it on the machine, and then type this in. You know why it's too, that's also a cool thing, why it's that's very abstract. Okay, so that's sort of one element that you'll probably need to have some background in. Again, if MATLAB is not sort of what you're experienced in, but you have programmed before, that is probably okay. I would just recommend that you take a tutorial on MATLAB, and in fact there's a tutorial on MATLAB that is linked to from the website. The second thing that we're going to use here is linear algebra. And so, again, it's pretty simple linear algebra. We're not doing anything too complex here, but really almost everything we write is in terms of vectors and matrices. It just makes for much more compact notation than writing things out element by element. And so we're going to use linear algebra extensively throughout this course. And so probably this could be pretty tough if you've not seen linear algebra before at all. I'm guessing most people have here, but that would be a requirement, some experience. Again, there are some review notes about this on the web page, and the type of linear algebra we actually use is quite simple. So take the problem like this, right? The problem where this notation here means that these are n-dimensional real value numbers. So R here means real value numbers, and it is a vector of elements. And you think of a vector as a column vector. A matrix that has one column, then n dimensions. And A here is a matrix in R n by n, which just means that R is A takes on elements the real values, and there's n by n of them. So you'll know how to solve for x in this equation. How do you do it? Yell it out. Yeah, so you group things alongside. Say ax plus x equals c equals c. How do you solve for x then? I know someone knows. Are you just not saying it? Can you just raise your hand maybe if you know how to solve this? Okay, everyone raise their hand. So what you do is x by itself is sort of like the identity times x, right? So you can also write this as a plus the identity times x equals c plus b. And then to solve it, you multiply both sides by the inverse of this. So x equals a plus I inverse times c plus b. That really is the level of linear algebra we're going to use in this course. Maybe a little bit more because we do things like take derivatives sometimes, but I'll explain all those things that we're going to do when we do them. And other than that, I mean, optimization is really formulated on linear algebra. So if you know this sort of background, I will try to be as light as possible, kind of the heavy-duty optimization. We'll talk about it much more from a practical perspective. So just how do you actually implement these things using existing libraries. And as I said, they're also on the website. Didn't plug in my computer. There are also on the website some notes on the linear algebra material that we need to learn for this course. Is there a plug here? Okay, so that's for prerequisites. The last thing then is, everyone knows how many characters are in my password now. Some bit of entropy has been decreased there. whatever it is, increase, decrease. Okay, so that's it for prerequisites. Then the next thing, and the last slide I have here is actually, it's going to be about the requirements for the class. So what does the actual assignments involve? The assignments, there's going to be 4 problem sets. These are going to be out every 2 weeks, with the first probably out a week from Thursday. There are going to be about 2 programming problems per set. There are going to be 4 to 5 questions, 1 to 2 programming problems. In addition, there's going to be 1 to 2 advanced or extension problems on these things. And this relates to what I said before, what I sent out an email about and what's on the website about 2 different versions of this course. So this course is listed under both 830 and 630. The reason for this is that we taught this course before once, or a version of this similar course at least, and there was a very sort of bimodal distribution of students, right? So some people kind of were experts already in some computational methods, and some were sort of more coming from it from other perspectives and wanted to learn a lot, but maybe didn't have quite the background. And it was a little bit unfair to kind of lump these all together. So we have 2 courses now. So the 830 version is the PhD level course, and that's going to include a little bit more advanced programming assignments, and the final project is also going to be a little different, which I'll get to in a second. But the point is, the reason for these 2 courses are to account for different backgrounds of people, right? This course is striving to be kind of a catch-all in that it should appeal to people that are interested in energy and maybe have the computational background but haven't explored energy very much. And also interesting to people who maybe come from the energy space and know these things really well, but don't really have a good background in computational methods applied to these things. Or people that want to learn both things, by all means. So it's really kind of trying to do a lot, and for that reason we're separating out into 2 courses. If you have any question about which one to take, talk to me. I know it's past the ad deadline, but I can sign any forms or help out if there's any kind of issues about which one you're assigned, or worries about which one you're assigned to. So just come talk to me about that if you have any questions. The last thing is the final project. So there is a final project in this class. There's no midterm, no final test, final exams, but there's a final project, and that's going to be an 8-page, at most 8 pages. Sorry, 5 pages. At most 5 pages. Oh, I said 8. Of a written report on some topic relating to a computational approach to energy. And we can do this in groups. So groups are going to be done in groups of 2 to 3. You can do it by yourself too if you actually want to, but you can also do it in groups if you want. And the difference between the 2 levels of the courses now is that for 830, this should be some original research piece. So it doesn't have to be a hugely original thing, but you should actually run some experiments and do some amount of sort of experimentation or research in a project like this. For 630, it can be more of a survey type paper. So you can just kind of look at a bunch of papers on a certain topic, see what they do, and focus on that. And all that I would say in addition to that is please come to office hours very soon if you don't know what your topic's going to be, there's a huge wealth of topics that are possible. A lot of you probably will know exactly what topic's going to be, but if you don't, please come to office hours. They're going to be on Mondays, 2 to 3, my office that's on the website. We'll also have extra ones before our problem sets due too. But in general, it'll be Mondays 2 to 3. And come chat, come see about what you might think about for your project topic. The last thing, and I think I actually wanted to go through some items in the syllabus here. I think the one thing I might have missed yet was the homework policy. So homeworks, I said there's going to be 4 problem sets. Let me make sure I get the numbers right from what I wrote before. Where's I have the syllabus up here. So there's going to be 4 problem sets, and for the problem sets, you're allowed some number of late dates. So lateness, things happen. You can't always get something due on time. So for that reason, you have, and I'm going to make sure I get the right number here, you have 5 late days. So what that means is you can hand in assignments a total of 5 total days late. So if you use 3 late days for one assignment, you have 2 left for the other 3 assignments, right? So you hand it, just bring it back to my office by the time of the start of class. Then within 24 hours, count for 1 late day. After that, I'll count for 2, etc. After you use the 5 late days, we start taking off 20% for each late day you use after that. So do try to get those in within those 5 late days. Don't go over that. But I also know people, you might have 5 assignments due on the same day, so I want to allow some flexibility there. Finally, you are allowed to work on the homework in groups. So you can do it in groups. And actually, am I getting late here? I don't want to run too late. Okay, I have some time. You can do the homework in groups. What you need to do, though, is you can work on the problems. They're sort of challenging problems, and I think that actually one of the best ways to learn is to talk through things with other people. And so working in a group can be really beneficial for that. So by all means, work in groups on the homeworks. And these policies are all laid out in the syllabus, I should add, too. But when you're working in the group, talk together, write on the board, whatever. Then go back to your house and write up, or your dorm, and write up the solution yourself. And this goes for programming assignments too. So your final just transcription of your, don't look at your notes you were taking when you actually were in the group. Go put that all aside, now that you understand the question, and write out the answer yourself. And also on the assignments, please do indicate which people you worked with in your study group as well. I think that is everything that I wanted to talk about today. As I mentioned, as you'll notice, there's a video camera here. We'll be videotaping all our lectures. They'll be online. Ideally, after the first day of class, maybe this first day, it'll take me a few tries to get it right. But they'll be available as a resource for you to go back to and refer to. And I think that's it. So I'm going to stop recording now. We have about 8 minutes left.